Basically, we're in a situation today where we have very small, very powerful electronics that exist thanks to economies of scale in things like the mobile phone world. We have cameras, sensors, computers that are getting smaller and smaller. Thanks to innovations also in personal electronics, we have batteries that are very energy dense, and that's only getting better with the work on electric cars and now solar panels probably coming up. We have this ability to take a sensor and put it in places where it would be really expensive or dangerous or risky to put a human. So if we want to inspect a building or map a field or go out and deliver a care package or a safety equipment in a dangerous place, we have the ability to do that from the standpoint of the electronics. What we've found is lagging behind is the platform to do this. So as long as we're talking about going up the facade of a building or a crane and doing an inspection, which is just a short vertical flight, then a quadcopter's fine. You've got a highly energy intensive system where you've got these rotors going all the time just to react gravity. And for a short mission, that's okay. Even then, making the airframe lighter is still an advantage, and we're dealing now with quadcopter companies that are using our technology. But where the gains lie is in being able to go further with these payloads. So with the same battery, with the same electronics, having a reliable platform that's low drag, high efficiency, which can fly for 2 hours, 3 hours at a time, whether that's loitering over an area, covering a grid, or A to B. Having that range just opens up the possibilities. It means you can now do even more with these payloads, and you can do away with a manned helicopter or a manned aircraft that has expenses associated with it, that has certain safety concerns that may not necessarily be there with an RPAS. So what we bring to the table is this ability to create a lightweight, efficient airframe that again behaves aerodynamically in a particular way. We have expertise in aeroelastics, so knowing that any deflection in the wings, in the body, is going to be to our advantage. We're able to use additive manufacturing to tailor the structural properties to exactly what we want, and whether that's the stiffness of the airframe or the resilience to attacks from birds, which apparently is a problem. It's just an ability to take these payloads further, and that's what we can do. And we can tailor that exactly to what the mission profile is. So again, when you design an aircraft, you start from the mission and the payload, and you design around it. So you know how far you have to fly, you know the conditions, and that basically dictates the size and the scale and the shape of the aircraft. Very analogous to a yacht, again, where you have an artificial set of constraints. There might be a length and a width, and then you have to design within them.